right, welcome. Today, we're doing something a little different, a deep dive tailored just for you.
Oh,
Yeah, you mentioned you're really interested in linear logic,
right.
but, and this is key, you're coming at it from a philosopher's point of view.
Makes sense.
So we're using the Stanford Encyclopedia of Philosophy entry on linear logic as our main guide here.
Good choice. Very thorough.
But think of this as a conversation, not a lecture. You know, we're going to unpack some pretty dense stuff, but hopefully make it fun.
I like that.
Now, linear logic. It's not your grandpa's classical logic, and it's not just about proofs, like intuitionistic logic.
It's a different beast altogether.
Right. Formulas are treated as resources, things you use up.
Yeah, and that has huge implications, changes how we think about inference itself.
Totally. And mastermind behind all this, Jean-Yves Girard, back in 1987.
Pivotal figure.
So, our mission, should we choose to accept it, is to break down linear logic's core concepts, connectives, rules, the whole shebang, and see what makes it tick, philosophically speaking, for you.
Sounds like a plan.
But before we get ahead of ourselves, where did this whole thing even come from? What sparked it?
The origin story. Well, Girard was deep in the weeds with models of System F. It's this super expressive system in computer science, all about describing how data is structured and transformed. Super powerful stuff.
Okay, so pretty technical beginnings.
Yeah. But beyond that, you can see linear logic as trying to bridge a gap. You've got classical logic, all elegant and symmetrical, focused on truth.
Right, the classics.
Then you have intuitionistic logic, all about constructive proofs. Girard wanted to reconcile these two, find some common ground.
A grand ambition, trying to bring those two worlds together. How did he even begin to tackle that?
Well, the core fragment, MEL, multiplicative additive linear logic, that came from two big aha moments. The first was about sequent calculus, which is a way to formally present logical arguments.
Okay, got it.
Now, in classical logic, connectives like and, or, even the cut rule, they could be expressed in two ways, additive and multiplicative. Additive means your different premises rely on the same assumptions. Multiplicative means they use separate sets of assumptions.
Gotcha.
But, and this is crucial, in classical logic, those two forms were basically the same because of these things called structural rules.
Interesting.
Yeah, so you've got contraction, which lets you duplicate assumptions, and weakening, which lets you just toss them out.
So those rules kind of smooth over the differences, make everything equivalent.
Exactly. It's like they're making implicit assumptions about how logical entities work.
Like hidden rules of the game.
Right, and that leads us to the second big insight. Gensen, he showed that non-constructive proofs, the ones that just prove something exists without showing you how to find it, those often use contraction or weakening in the succeedant.
The succeedant meaning?
The right side of the logical derivation, the conclusion part.
Ah, right. Okay.
So Girard thought, if I want a more constructive, resource-aware logic, but I still want some of that symmetry.
You got to get rid of those rules.
You got it. But when you ditch contraction and weakening, those additive and multiplicative forms of the connectives, they become totally different things.
Oh, wow. So and isn't just and anymore.
Nope. Now you've got the additive with and the multiplicative tensor. Same with or, now it's plus and spar. It's a whole new world.
A logic where and has two meanings. That's wild.
It is. And it actually helps us understand the difference between classical and intuitionistic logic better. Think about the law of excluded middle. You know, A is true or not A is true.
Right, the classic.
Classic, but intuitionistic logic doesn't like it. It wants proof, not just possibilities.
Okay.
Now, in linear logic, that law splits in two.
Yeah.
A plus neg A is the additive version, and it's not provable in general. That's intuitionism right there. You got to choose between A and not A. No freebies.
Makes sense.
But then there's A mulpart neg A, the multiplicative version, and that's totally provable, just like a right arrow A.
Hold on. How can both versions of excluded middle exist in the same system?
It's because they're talking about different things. The additive plus demands a choice. But the O par, the multiplicative par, it's about compatibility, not choosing. It's like saying A and not A can coexist without messing things up.
Mind blown. So it's not just about true or false anymore. It's about how those truths interact.
Exactly. And that brings us to negation. Linear logic keeps it involutive, so double negation gets you back to where you started.
Okay, that seems pretty standard.
Yeah, it feels natural. But the sequence, the way we write out logical arguments, they're symmetrical in linear logic. Assumptions and conclusions are balanced, unlike intuitionistic logic, which is kind of lopsided.
So linear logic is all about balance and symmetry.
In a way, yeah. But remember, we talked about formulas not being truth values anymore.
Yeah, because you're using them up.
Right. They're resources now. So say you have a proof of A, right arrow B, in linear logic that's A bot par, and you also have a proof of A.
Okay.
If you combine them to get B, you've used those proofs up, they're gone, spent.
It's like to prove something new, you got to spend the proofs you already have.
Precisely. It's logic with a built-in cost. Every assumption, every inference, it all adds up. You can't just copy-paste proofs infinitely.
Wow, so you really got to be mindful of your resources in this logic. But doesn't that limit what you can do?
It does, and that's where the exponentials come in. These are like special markers, bang for of course, and why not, that let you break the rules sometime.
Break the rules.
In a controlled way. If you put bang on an assumption, you can use it as many times as you want.
So you can duplicate it.
Yeah, and you can even ignore it if you need to. And Quest is the same thing for conclusions.
So it's like selectively turning off the resource restriction.
Precisely. It's a way to control when you're being super strict about resources and when you can be a bit more relaxed.
That's clever, having the best of both worlds.
Exactly. And it's actually how you can embed classical and intuitionistic logic within linear logic.
Oh.
Yeah, so it's not just about those core fragments like MEL. You also have MLL, which is just the multiplicative connectives, and MEL, which adds in the exponentials, but not the additive stuff.
Okay, so there are different levels of linear logic depending on what you need.
Right, and don't forget the intuitionistic versions, IMLL, ML, IML. There are whole families of these systems.
Yeah.
And they all connect back to classical logic in precise ways.
A whole logical ecosystem. It sounds like linear logic didn't appear out of thin air, though.
Definitely not. It has roots in these things called substructural logics. They came before linear logic, and they were already messing with those structural rules we talked about.
Ah, so linear logic is part of a bigger family.
Exactly. There's the Lamb-Beck calculus, which cares about the order of your assumptions. There's relevant logic, which says every assumption got to be connected to the conclusion. And there's affine logic, which is like linear logic, but allows weakening.
Lots of different ways to tweak the rules of the game.
Yeah, and linear logic kind of brings all these ideas together in a really powerful and systematic way.
Okay, so we've got the motivation, the history, and the whole resource thing.
Hmm.
But how do you actually use this logic? What do the proofs look like?
Well, remember the additive and multiplicative connectives?
Yeah, the two kinds of and, or.
Right. They're key to the proof systems.
Yep.
So classical conjunction and its top element, they split into the additive side and one for the additive side.
Right, so you've got 4 different symbols now.
And it's the same for disjunction. Classical VN bot split into oplis and 0 for additive,
Okay.
and bot for plicate. All these different symbols let you analyze logical structure in much finer detail.
Got it. So what about negation? You said it's involuted, right?
Yeah, it's written as a bot for a formula A. Sometimes it's treated as a basic connective with its own rules.
Makes sense.
You can introduce it on either side of the sequent depending on whether A is there or not. But you can also define negation just for atomic formulas, and then use De Morgan's laws to get the negation of bigger formulas.
Oh, because those laws tell you how negation interacts with the other connectives.
Exactly. And then you can define linear implication, B limp C, as B bot C. It's all connected. Even intuitionistic implication, B right arrow C, you can write that as bang, B limp C.
Wow, so you can express all these different types of logic within linear logic. That's pretty neat.
It is. Now, those exponentials, bang, they're called exponentials for a reason, you know?
Because of how they distribute.
Yes. They act kind of like exponents in algebra. For example, bang B amp C is the same as bang BO times bang C.
Okay, so they follow similar rules.
Yeah, they distribute over the connectives just like exponents distribute over multiplication and addition. It's pretty elegant.
It is. So how do proofs actually work in linear logic? What's the formal system?
The main system is a two-sided sequent calculus. Remember how we said sequents have assumptions on the left and conclusions on the right?
Yeah, with a turnstile in the middle.
Right. But in linear logic, those sides are multi-sets of formulas.
Multi-sets, meaning...
It's like a set, but you can have the same element multiple times.
Yeah. So the number of times a formula appears actually matters?
Exactly. That's because we're dealing with resources. You got to keep track of how many you have.
Right, of course.
So the calculus has the usual identity rules like the axiom rule, V-B,
Okay.
and the cut rule. But the big difference is with weakening and contraction.
Because you can't just use them willy-nilly anymore.
Right. You can only weaken or contract formulas that have the bang or quest modality.
So those exponentials really control the flow of resources.
They do.
Yeah.
And even the rules for introducing those exponentials are picky.
Picky how?
They have preconditions, like in modal logic. Sometimes the whole context has to be filled with reusable formulas for you to use them. It's all very controlled.
It sounds like a very meticulous system.
It is. But the good thing is, the cut rule is eliminable. You can get rid of it without losing any deductive power. And the axiom rule, you can mostly eliminate that too. It makes things much cleaner.
A very streamlined logic.
Yeah.
Now, you mentioned focused proofs earlier. What are those?
Ah, yes. Focused proofs are a way to organize proofs in linear logic, a kind of normal form. They were introduced by Andreoli back in 1992.
Okay.
The key idea is that formulas are split into two types, asynchronous and synchronous.
Asynchronous, synchronous. Those sound familiar.
Yeah, they're used in other areas of computer science too. Basically, asynchronous formulas are the ones you can just apply rules to without worrying too much.
So they're kind of safe to work with.
Yeah, their rules are invertible. Like to prove B and C, you just prove separately.
Easy peasy.
Right. But synchronous formulas, those are more delicate. Applying their rules might break your proof if you're not careful.
So you got to handle with care.
Exactly. Like to prove the unit 1, you need all your assumptions to be gone. It's very context sensitive.
Sounds tricky.
It can be. So focus proofs give you a strategy. You have an asynchronous phase where you apply all the easy rules first.
Got it.
And then a synchronous phase where you focus on one synchronous formula at a time and apply its rule carefully.
Like a two-stage process.
Yeah, and the focus proof system visually separates these phases. You have different zones for reusable formulas, linear formulas, and the one you're focusing on.
So it's a very visually organized system.
It is. And the cool thing is focus proofs have been adapted to classical and intuitionistic logic too.
Oh, really?
Yeah, it shows there's a deeper connection between these different logics at the proof level.
That's fascinating. So focus proofs are like a roadmap for navigating the complexity of linear logic.
Mm-hmm.
Now, you also mentioned proof nets as a way to represent proofs. How are those different?
Proof nets. They're like a whole different way of visualizing proofs, especially for MLL, the multiplicative fragment.
Okay.
See, with sequent calculus, you have to write proofs step by step, even if the order doesn't really matter logically.
Right, it's very linear.
Exactly. Proof nets get rid of that. They're graphs, so they show you all the logical dependencies at once, without imposing an arbitrary order.
So it's a more holistic view of the proof.
Precisely. You can see the whole structure at a glance.
Neat. So how do you go from a sequent calculus proof to a proof net?
It's done inductively, based on the last rule you applied in the sequent calculus proof.
Okay.
So, for example, an axiom rule in sequent calculus becomes an axiom link in the proof net.
Connecting the two identical formulas.
Exactly. A cut rule becomes a cut link. And the multiplicative connectives, they have their own special links too.
So formulas become nodes and rules become links.
You got it. It's like a wiring diagram for your proof.
I like that analogy.
Right.
But how do you know if a proof net is actually correct if it represents a valid proof?
That's a big question. There are a few criteria you can use. Girard came up with the long trip criterion and the ACC criterion,
Sure.
AC-click connected. But those can be computationally expensive to check.
Not very efficient.
No. The best one is called contractibility. It's a graph parsing criterion, and you can check it in linear time.
Much better. So what about cut elimination? How does that work in proof nets?
It's beautifully simple. It just becomes local graph rewriting rules.
You just change the graph a little bit.
Yeah. For MLL, you have the axiom move, which deletes a cut between two axiom links,
Okay.
and the multiplicative move, which deletes a cut between a tensor link and a par link.
And those moves always preserve the correctness of the proof net.
Always. They're like little surgery operations that clean up the proof, and they directly correspond to cut elimination in sequent calculus.
Amazing. It sounds like proof nets are a much more elegant way to handle cut elimination.
They are, at least for MLL,
Yeah.
but when you try to extend them to the full linear logic, things get tricky.
Oh, why is that?
The exponentials are the main problem. Girard used boxes to represent them, but those boxes make things more complex.
They're not as local anymore.
Right. And the reduction rules are more complicated. There have been other attempts, like coherent spaces for sharing proof nets, but it's still an open area of research.
Always more to discover. Now let's talk about semantics. How do you assign meaning to linear logic?
There are two main approaches, semantics of provability and semantics of proofs.
Semantics of provability, that sounds like figuring out when a formula is actually true.
Exactly. You create mathematical structures that interpret the formulas and tell you which ones are provable.
Like a model of the logic.
Yes. One way is to associate each formula with the set of contexts it can be proven from. Girard's phase semantics is a good example. It uses monoids and sets of phases to give meaning to the formulas.
And what are those used for?
They're used for all sorts of things: finding counterexamples, analyzing concurrent systems, even proving cut elimination in a different way.
Wow, very versatile.
Right. There are also Kripke-style semantics, which use possible worlds and algebraic models based on quantales. Lots of options.
So many ways to interpret linear logic. What about semantics of proofs? How do you give meaning to the proofs themselves?
That's where the computational aspect comes in. You see, in constructive logics like linear logic, a proof isn't just about truth, it's also a recipe for computation.
So the proof itself tells you how to do something.
Exactly. And semantics of proofs is all about understanding what that something is.
Yeah.
One way is to use relational semantics. You interpret formulas as multisets, sequence as tuples of multisets, and proofs as relations between them.
So you're basically tracking the flow of resources through the proof.
Yeah, you see how the multisets change as you apply the rules. It's a very dynamic view of proofs.
Makes sense.
There's also an approach using coherent spaces, which are sets with a special relation. And then there's category theory, which provides very abstract models for proofs.
Category theory, always abstract.
It is, but it's also very powerful. It captures the essence of duality and resource management in linear logic.
And what about Girard's geometry of interaction? That sounded pretty wild.
Oh, yeah. It's a very algebraic way to think about proofs, especially proof nets. You assign matrices to the cut links to represent the flow of control.
Okay.
And then you have this execution formula that describes the whole proof. It's invariant undercut elimination, which is pretty amazing.
So it captures something fundamental about the proofs, something that doesn't change when you simplify it.
Precisely. It's like a fingerprint of the proof's computational content.
Very cool. Now, lastly, you mentioned game semantics. How do games relate to linear logic?
That's a deep connection. There are two main ways to think about it. One is dialogical games, where you have a prover and a refuter arguing about a formula.
So like a debate.
Exactly. The rules of the game correspond to the logical rules, and if the prover has a winning strategy, the formula is provable.
Interesting way to think about it.
The other way is to think of formulas as games themselves. Each connective is a way to combine games, and proofs are strategies for playing those games.
So logic becomes a game.
In a way, yeah. And this approach is really good for understanding programming language semantics. It's called full abstraction, when the game semantics perfectly matches how the program behaves.
Wow, so games are a powerful tool for understanding both logic and computation. This has been a whirlwind tour of the semantics of linear logic. But now let's talk about complexity. How hard is it to actually work with this logic?
That's a key question. For MLL, it's NP-complete.
NP-complete meaning?
It means you can check a solution quickly, but finding one might take a long time.
So it's not easy.
Not always, no. For MAL, it's even worse. It's PS-based complete.
So that's harder than NP-complete.
Yeah, it means you might need a ton of memory to solve problems. The memory can grow exponentially with the problem size.
Yeah, I guess.
And what's crazy is even if you just use constants, no variables, it's still that hard.
So the complexity is really baked into the logic itself.
It is. And when you add exponentials with MEL, things get really hairy. It turns out MEL is connected to the reachability problem for branching VS, vector addition systems with states. It's a really hard problem in computer science. And people are still arguing about whether MEL is even decidable.
Decidable meaning?
Meaning there's an algorithm that can always tell you if a formula is provable or not. Some people say they have a proof. Others say those proofs are wrong.
A real mystery. So what about full propositional linear logic? The whole shebang.
That one's undecidable, for sure.
No algorithm can solve it.
Nope, not in general. But there's been a recent claim that it might be decidable after all.
There's a controversy.
Yeah, it's still up in the air. But linear affine logic, which is linear logic plus weakening, that one is decidable.
So adding weakening makes it easier.
In a way, yeah. It's still computationally expensive, but at least it's decidable.
Okay, so the complexity of linear logic is a bit of a wild ride.
It is. But despite all that, it's had a huge impact, especially in computer science.
Right, because it's so good at handling resources.
Exactly. And it gives you a whole new way to think about computation. While intuitionistic logic shook things up in math, linear logic is really making waves in computer science. You see, there are two main ways logic is used in computer science: computation as model and computation as deduction.
Can you explain this?
Sure, computation as model is when you use logic to describe a computational system from the outside.
Like a meta language for talking about computation.
Exactly. Linear logic hasn't really been that successful in that area.
Right.
But computation as deduction, that's where linear logic shines. It says that computation is fundamentally about deduction, about proving things.
So the logic itself becomes the computation.
Precisely. And there are two main branches there: proof normalization and proof search.
Can you break those down for us?
Sure. Proof normalization is about simplifying proofs, like we talked about with cut elimination. Think of it like running a program in a functional language.
Okay, so the steps of simplifying the proof are the steps of the computation.
Exactly. And linear logic gives you this really neat way to track how resources are used during that simplification.
Because every step has a cost.
Right. It also lets you formally capture the duality between a function and its environment.
Environment being.
The context the function is running in.
Yeah.
For philosophers, this could be really interesting. It's like a formal way to talk about agency and context.
Like how an agent acts within a specific environment.
Precisely. Linear logic has also helped develop optimal reduction strategies for the lambda calculus, a fundamental model of computation. So linear logic is helping make programs run more efficiently.
That's pretty impressive. And this whole idea of resource management in computation, that could have philosophical implications too, right?
Absolutely. It makes you think about efficiency and how we reason in general. There's also a deep connection between linear logic and the idea of a function and its environment as dual entities.
Dual meaning.
Two sides of the same coin. They define each other, they're interconnected. This connects back to philosophical debates about subject-object relations and how internal and external factors interact.
Very profound.
It is. And linear logic has even been used to design type systems that can guarantee certain computational properties.
Like what?
Like ensuring that a program runs within a certain time limit. It could be relevant to philosophical questions about the limits of what we can compute, maybe even the physical limits of thought itself.
So many philosophical avenues to explore. What about proof search? How is that seen as computation?
Well, in proof search, the computation is the process of searching for a proof. It's like exploring a maze, trying different paths until you find the exit.
And logic programming is based on this idea, right?
Exactly. And linear logic brings some really cool new tools to logic programming. It gives you new logical connectives and a way to express concurrency.
Concurrency meaning.
Multiple things happening at the same time. And remember, focused proofs.
Yeah, the two-phase system.
Well, they give you a really clear understanding of how logic programming works in a linear logic setting. You can see the different phases of the search process, like goal reduction and backchaining.
So linear logic provides a deeper explanation for something that's already used in practice.
Exactly. It's not just theoretical, it's very practical too. And because linear logic uses multisets, it can also model multiset rewriting systems.
Great chart.
Systems where you have a bunch of elements and you can rewrite them according to certain rules. They're used to model all sorts of things, like concurrent systems, processes interacting with each other, even security protocols.
Wow, so linear logic is a very versatile tool for understanding different types of computational systems.
It is. It gives you a way to formalize concepts like interaction, change, resource flow, maybe even causality and agency.
So many possibilities.
Yeah.
Before we wrap up, you mentioned some variations of linear logic that could be philosophically interesting.
Yes. There are lots of ways to tweak linear logic to explore different ideas. For example, some people are studying non-canonical exponentials, which have different properties than the usual ones.
So different ways to control resources.
Exactly. And there's a debate about whether MEL with multiple exponentials is decidable. It gets at deeper questions about modality, about necessity and possibility.
Very philosophical.
It is. Then there's non-commutative linear logic, which is sensitive to the order of assumptions.
Meaning?
It means the order you use the assumptions in actually affects the outcome. It could be relevant to discussions about time, about the importance of sequence, maybe even the logic of storytelling.
Fascinating.
Right. And then there are fixed point operators, which let you express infinite processes directly within MEL. It's a different way to handle infinity and self-reference, which has always been a hot topic in philosophy.
So many avenues for future exploration.
Uh-huh.
This has been an incredible deep dive into linear logic.
It has.
We started with the basic idea of formulas as resources and saw how it leads to this rich structure, with different connectives and carefully managed rules.
It's a very elegant system, despite its complexity.
It is. We explored the different proof systems, the semantics, the computational complexity, and even some of the philosophical implications.
And we saw how linear logic is shaping our understanding of computation and providing new tools for logic programming.
It's a truly fascinating and powerful area of logic. So
Mm.
for you, our listener, here's something to ponder. How could this idea of resource consciousness change how we think about fundamental philosophical problems?
It's a great question to consider.
Could it give us new insights into being, becoming, interaction? This deep dive is just the beginning. There's so much more to discover.
There really is.
Check out the bibliography and the related entries in the Stanford Encyclopedia of Philosophy if you want to learn more. Thanks for joining us on this journey.
It's been a pleasure.